and good evening, everyone. So we'll be really covering 15.7 today, triple integrals, and 15.8, which gets into cylindrical integrals. Before we do that, I thought we could warm up with just a center mass problem from 15.5. That was the last thing we did. We had to find either the mass or the center mass. This row of x, y, just remember that's the density. That's the density that they're talking about, so that's what that row of x, y is. And if we do x bar, we do 1 over the mass, double integral, then you have that x, 1 over mass times this. Or you can think of it as 1 over mass, we say times the moment. X bar is 1 over the mass times the moment about the y-axis. Y bar is 1 over the mass times the moment about the x-axis, but this is what comes out. I wanted to do one like from the practice problems, the problem set. I wanted to do a problem like number 12. They go, so I'll change up. I'll make different radii. Can you find the mass of a lamina? So hey, good news, everyone. We're just going to find the mass of a lamina. That lamina is just a thin plate that lies between two circles. And how about r equals 2 and r equals 4? All right, radius 2 and radius 4. These circles are centered at the origin. If the density equals the reciprocal of distance from the origin. Now I'm going to use that same expression for the density. We're using the same density. If the density equals the reciprocal of distance from the origin. And maybe some of you have already worked the problem with the radius 1 and 2, but I thought it'd be good we start with this problem today because the reason, number 1, it allows us to update what we did last lesson. Number 2 is today we'll do center mass of a solid. Let me say it again. We'll find center mass of a solid, like a sphere. This is just a lamina, very thin plate. So when it comes to a solid, we're gonna need a new formula. Because this only gives us center mass of some lamina, some thin plate. Like you can almost think as thin as this paper. We're talking about something like a solid, like an object. But anyways, if we only need the mass, all I need is a double integral of the density. Right? Where this is D, but let's draw D, this region of integration. Two circles, radius 2 and radius 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This is your region of integration. They didn't say like half circles or a half donut, like a half donut. This is like a donut, isn't it? There's your donut. So just by this being the region of integration, this is D. Do you agree we should go polar? We should use polar coordinates whenever the region of integration deals with circles. Let's go polar on this. So right away, let's go polar. All right. What letter can we not forget? See it? Now when we say when we go polar, it's always RD theta equals the dA. RD theta. We need that R automatically every time we go polar. So I'm going to put that down before I forget it. I'm just going to put it right here. Just R, don't forget R, and then dRd theta. All right. What's the limits for the radii? Yeah, nothing tricky about that. Everyone, the radius is 2 to 4 then. In that entire region, right? 2 to 4 there, 2 to 4, 2 to 4, 2 to 4, 2 to 4 throughout the whole image. Easy. What's theta? All the way around. 0 to pi? Boom. This problem's looking all right. But what about the density? We're going to put the density here. density was reciprocal, that means 1 over, right? Okay. 1 over. Distance from origin. What the heck is distance from origin? Distance from origin is, right, isn't that distance from origin? If that's distance from origin, I gotta put that down here. But then I gotta make it polar. What does that turn into? 1 over the square root of r squared, which simplifies, doesn't it? So what's that whole mess turn into? It really gets nice. Just drd theta, that's r over r1. So we just have an integral from 0 to 2 pi, 2 to 4. This becomes a 1. If you want, you can split this thing up, right? I can do 0 to 2 pi and theta. And I can multiply that times the integral from 2 to 4 of a 1 dr. The integral from 0 to 2 pi d theta is, you get theta from 0 to 2 pi, you just get 2 pi, right? What's the integral of 1? Or you go from 4 to 2, what's 4 minus 2? 2, final answer? There's your mass. So that would be the mass of that lemma. I just thought it'd be good to start with that. Didn't take much time, but what it does is when we get to solids later, you're going to be able to go, oh, it should be something like this. But it won't be a double integral anymore. So now we're getting into what we call triple integrals. Is everybody go with that? Yeah. Nice. Good deal. Okay. I can erase. We haven't seen triple integrals yet, so we're going to figure out what the heck this is for. What's the reason behind triple integrals? One is going to be, it's necessary to find the center of mass of a solid. That's one reason. You can find the center mass of a solid. That's a great application problem, but it also makes it really easy to find something like volume. So we're not going to work this problem. But when I saw this problem in the book, they go, this was back in section 15.2. So if this was in section 15.2, this problem, we didn't learn triple integrals yet, right? But they go, can you find the volume of the solid that lies underneath this hyperbolic paraboloid, z equals the 3 minus y squared, 3y squared minus x squared plus 2. 3y squared, 3y squared minus x squared plus 2. So this is just a lead into what we're going to be doing in a second. This is back in 15.2. Can you find the volume of a solid that lies underneath this paraboloid, hyperbolic paraboloid, and above the rectangle, so this is where we'll set up our limits of integration. Above this rectangle, they said -1 to 1 by 1 to 2. Well, we won't solve it, we'll just set it up. Oh, this, by the way, when you write it like this in the textbook, that's the x, there's limits for integration for x, that's the limits of integration for y, and this would be over a rectangle. So these are x's, these are y's. You want to go dy dx? And this is how we found volume. We just set double integral of the expression right here. dy squared minus x squared plus 2. And -1 to 1 for x, and 1 to 2 for y. And you work it out. Hey, I'm curious, this has 4 constants. Can I split that up? I always like when if you see what you have to do as an iterated integral. Okay, he goes iterated. Very good. Although it has 4 numbers, I still have to do this as an iterated integral because you can't factor this so that you only have product of y's with a expression of x's, like x times y. But we got it. But is there a way you can look at this in section 15.7 with triple integrals? You wouldn't need it here, but we're saying, well, you could have done this. You know, like this. All right, 1 to 2. to do now integral here. And this will be my upper z, this will be my lower z. And I'm talking about surfaces. Because to get the volume, I'm like the volume bounded by these two surfaces. So this would be the top surface, this hyperbolic paraboloid, that would go right here. I just thought this would be a good lead into what's going on in section 15.7. I could set up the problem like this. What would be the lower bound though? See, when I wrote this, everyone, let me read this again. They just go, this is a problem of 15.2. Find the volume of the solid that lies under the hyperbolic paraboloid, z equals 3y squared minus x squared plus 2, and above this rectangle. Well, this rectangle, above this rectangle, where was this rectangle lying? It was lying in the xy plane. The xy plane is the equation z equal to 0. Someone got that? So I want to point that out. This rectangle above this was lying in the xy plane. So we can set this up where this is just z equal to 0. You go, now what goes here? Just a 1. And this is what we're looking at today, 15.7, triple integrals. So aha, double integrals found volume. Double integrals find volume if your expression right here is the function, z function of x and y, and you know what else has to be true? I remember we talked about this. The function of x and y would have to carry on positive values over that region. You can't go negative if we dip underneath the xy plane. But triple integrals also find volume. Do you notice that? But triple integral of what number? What number is that? 1. So I'll be saying that often. Okay, a triple integral, when you have a 1, will always find volume. So that can be confusing, because you're like, well, double integral of a 1 would actually just be the area. But double integral of a function here, as long as that function of x and y, I'm going to put z, I'm going to make a note. As long as that function of x and y is always greater than or equal to 0 over that region, which it is, then it's going to give you volume. But we can call it net volume because sometimes we know this. Don't planes and surfaces dip below the xy plane and stuff? Yeah. So in this case, I get this 1. We can work out a problem. Can you take me through the first integral? What's the integral of this with respect to z?
It's a z.
You just get a z. And what's the top limit? Square minus x squared plus 2. And?
0.
0. And you plug this in, and guess where you're at now? Ta-da! See what happens? Ta-da! Da-da-da! You're now here. This and here. Subtract this. Now you're at this point. See how it goes together? But this is a wonderful way for us to set up problems from now on. Because we're like, oh, I want to get the volume bounded by this paraboloid and this paraboloid. Okay, whichever one's up on top, in terms of like higher, and which one's below, bounded below, upper, lower, and put a 1. And we'll give you the volume between those solids. Cool? Alright. So, on that note, triple interval of a 1 finds volume. So, this problem we won't solve. We're going to solve the one after this. Can you just set this up? Set up an expression that finds the volume. How do you work this? Of the region. Volume of the region in the first octant bounded by these planes. Um, 8x plus 2y plus z equals 4. That's one plane. The next plane, x equals 0, y equals 0, and the last plane, to set up the problem to solve this. But we'll set up a triple integral. Because triple integral of what will give us value? Triple integral of 1, right? Okay, so we're going to set up triple integral of 1. We're going to have to set the boundary. But what's the plane x equals 0? X equals 0 is the yz plane. What's the plane y equals 0? That's the xy plane. This plane z equals 0, that's the, like the floor here, that's the xy plane. But then you got this other plane. And so we should make a sketch to really see this. I mean, we really want to see the map before we set this thing up. So you're going to notice in section 15.7 with triple integrals, you will want to make a sketch a lot of times. A lot of times. You're going to want to make a sketch so you can visualize what's going on here in this first octave. So, you might recall this. There's x-axis, y-axis, z-axis. And I'm not going to draw the other axes because they just said first octave. So I might as well just, in terms of negative axes, I'll just keep all the positives. That's the positive x-axis, that's the positive y-axis, the positive z-axis. Do you remember how to sketch a plane? Can we sketch this plane? Intercepts. So let's sketch this plane right here. What's going on when x is 0 and y is 0?
Z is 4.
1, 2, 3, 4. Psh. What's going on when x is 0 and z is 0?
2.
Y is 2. One more point. Let's find the x-intercept. What if y and z both 0?
1.5.
Oh, it's a half. Okay. That's alright. X is 1/2. So plot this. 2, but this was just like right here. At 1/2. Well, I'm now going to sketch this. Looks like a triangle, doesn't it? It's the face of that plane. Psst.